Welcome to This Explainer. Today, we're diving into the absolute high-stakes world of systems engineering. We're going to figure out exactly how massive, mind-bogglingly complex infrastructure is kept running safely. I mean, think about the intricate railway networks that millions of us rely on every single day. How do we guarantee they don't just break down? Let's get into it. All right, so here's the thing. Designing a complex system, that is a monumental task. You build it, you test it, you finally flip the switch and turn it on. But the real challenge, that's keeping it dependable day in and day out. Asking, does it work and is it safe? Well, that's really just the starting point. We have to figure out how to maintain that dependability throughout the system's entire operational lifetime.
So here's our game plan for today. We'll start with the Dependability Balancing Act, then move into reactive and preventative maintenance, check out predictive maintenance, dive into reliability-centered maintenance, and finally wrap up with asset renewals.
Okay, starting right off with Section 1, the Dependability Balancing Act, and how we navigate the trade-offs. You know, every single maintenance decision an engineer makes requires a balancing act. It's a massive trade-off. If you intervene too often, doing really high-frequency maintenance, your costs absolutely skyrocket and you cause a ton of disruption. Basically, the trains can't run because you're always blocking the tracks to fix things. But on the flip side, if you intervene too rarely, you create a much higher risk of failure, and that severely compromises performance and, obviously, safety. That brings us to Section 2, reactive and preventative maintenance. These are really the traditional approaches to the problem. Let's start with reactive, or corrective maintenance. This is the most basic approach in the toolkit. You are literally just fixing what's broken after a failure has already happened. You wait for a component to stop working, and then, boom, you send someone out to repair or replace it. Now, I know what you're thinking. That sounds incredibly inefficient, right? But honestly, for non-critical components where a little downtime isn't a safety risk or a huge operational nightmare, simply running an item to failure is actually a completely valid choice. If a part is cheap to replace and its failure doesn't literally stop the train, you might just let it run until it quits. Moving a step up the complexity ladder, we hit preventative maintenance. This is where interventions happen on a strict, time-based schedule, totally regardless of the current condition of the equipment. It's exactly like changing the oil in your car every 5,000 miles, whether the oil actually looks dirty or not. And this fixed schedule, it is absolutely vital for exposed mechanical items. Think about the points machines on a railway track. These things have moving parts operating out in severe weather, day and night. They need regular lubrication and visual checks on a very rigid schedule to keep them from seizing up and causing total chaos. But there's a huge catch here. Sending staff out into hazardous environments, like live, active railway lines, just for routine checks, that exposes them to really significant danger. Plus, it disrupts train operations. And the crazy part is, a lot of the time, the equipment they are risking their lives to check was actually working perfectly fine. Which leads us nicely to Section 3, Predictive Maintenance and Remote Condition Monitoring. This is where we see a huge data-driven shift. So the real game changer here is shifting away from that time-based schedule we just talked about, where you're essentially just guessing when maintenance is needed, and moving toward a data-based approach. In this new model, you only intervene when the data explicitly tells you, hey, this is absolutely necessary. We call this predictive maintenance, and it's the absolute ideal proactive scenario. By detecting a potential fault before it actually happens, we can jump in and fix a component right before it breaks. It's amazing because this maximizes the lifespan of the asset while completely avoiding unexpected downtime and those frustrating delays. This whole strategy is powered by something called Remote Condition Monitoring, or RCM. By attaching tiny data loggers to the equipment, engineers can continuously track the real-time health of these components. So, instead of sending a human physically out to the track, the system predicts failure modes and lets you plan interventions right from a desk. To put that into perspective, imagine remotely monitoring the electrical current of a track circuit, or the operating speed of a points machine. If a machine suddenly starts drawing just a little bit more current to move, or it operates just a fraction of a second slower than normal, engineers get an early warning sign. It's a clear red flag that the component is starting to degrade and is going to need attention really soon. Moving on to Section 4, Reliability-Centered Maintenance, or how we optimize the toolkit. So with all these tools in front of us, reactive, preventive, and predictive, how do engineers actually decide which one to use on which piece of equipment? Well, that brings us to reliability-centered maintenance. Now, this isn't just a single physical action you do. It's an overarching strategic framework that dictates exactly how we deploy our entire maintenance toolkit across the network to perfectly optimize safety and performance. Here's how they do it. Engineers systematically follow a set of steps. First, they identify exactly how a specific asset might fail. Next, they assess the safety and performance consequences if that failure actually happens. Then, they look at the asset's wear-out characteristics, and finally, they customize the maintenance strategy specifically for that individual item.
In practice, this makes a ton of sense. It means a set of points located in a remote, low-traffic siting simply doesn't need the exact same rigorous, expensive maintenance schedule as the exact same machine located on a highly critical, high-speed junction. The consequences of a failure at those two spots are vastly different, so you intelligently focus the maintenance effort where it literally matters most.
And finally, Section 5, Asset Renewals, getting ready for the end of the life cycle. Because let's face it, no matter how perfectly we maintain a system, and no matter how good our data is, absolutely everything eventually reaches the end of its operational life. And that brings us to the ultimate step, renewals. This is the massive process of completely replacing aging assets before they fail catastrophically. It's just a basic reality check that maintenance alone can't overcome the physical limits of materials after decades of use.
Stepping in with a full renewal is absolutely critical. It prevents the system from entering this dangerous wear-out period where failure rates suddenly spike. Plus, it solves the huge problem of obsolescence. You have to ensure the system remains compatible with modern tech, and this is a big one, that manufacturers are still actually producing the spare parts you need to support it. But as we look ahead, we have to ask a pretty fascinating question. As remote condition monitoring and AI become incredibly advanced, what if we could predict degradation perfectly? Like, what if we only ever had to replace the exact microscopic subcomponent that needs it, literally moments before it fails? Could massive disruptive system renewals eventually become a thing of the past? Ultimately, the future of infrastructure dependability doesn't just lie in wrenches and grease, it lies in smarter data. By fundamentally shifting how we balance cost, access, and performance through predictive tech, we can keep our vital systems running safely and seamlessly. So the next time you're on a smooth, uninterrupted train ride, ask yourself, what invisible streams of data are working in the background right now to make sure you arrive safely?